Pam, yeah, the sound is on. Yeah, okay. So I should start by saying that I lied a bit to you. So the end of my first lecture, there was this diagram, C of Z to C of ZP. I think this is a thicker pen than I had, right? Going to this T of ZP. And here I had the T of Z and the closure of T of Z. And this C here, well, so what did this rely on? This came from another diagram. I had J here, and remember J was now over Z. It is the Néron model of the Jacobian over Q. This mapped to J times J dual not to the rho minus 1. Rho was this Picard number, and here I had P cross to the rho minus 1, the Poincaré torsor, but then pull backed by rho minus 1 projections to J times J dual not. And the pull back of that was called T. And then here I had C over Z, but to make the map from C to J, I mean, the universal property of a Néron model is that it is good for smooth schemes over Z to map to the Néron model. So I restrict to the open locus, the open subset of C. C was, remember, C was a model over Z of my curve over Q. And this model had a few properties. It was proper and regular. But it was not smooth. There can be primes of bad reduction. So if you want it to be proper and smooth, you have a problem. This is, you ask for too much. So there is this is the open subscheme of C, where C to spec of Z is smooth. Yeah. And this you can extend uniquely to a map to J, to the Néron model of the Jacobian over Q. And now I would like to lift this. I would like to do this to get this map here. But unfortunately, you have a problem. The problem is like this. We knew that we had set it up so that the pullback of this torsor to the generic fiber, to the curve over Q, was trivial. But the fibers, the problem, here I have a problem with primes, well, with primes Q such that the fiber of this C smooth over FQ is reducible. If that happens, so what happens is this. Suppose you have a line bundle on C over Q, and you know it is trivial. Suppose you have a line bundle on the C smooth, and that it is trivial on the generic fiber over Q. Then over Q you have a section with no zeros and no poles. This section has a divisor. It's a rational section of your line bundle. And so it has a divisor, and this divisor is concentrated. Well, it doesn't meet the generic fiber. So that means that the prime divisors that occur in these divisors are irreducible components of fibers. So how unique is your trivializing section over Q? Well, that is unique up to an element of Q star. And so by the unique factorization of integers, I can change this section by only one, well, at a prime Q, I only have Q to the something to change it. And that will change the divisor, the valuation of my section at the different generic points of the irreducible components in that fiber, all by the same number. So I can only move one to 0, and then the others are what they are. So that is a problem. And for that reason, we have to restrict to an open subset here before we can lift this. And what can you say about this open subset? So here we take open subsets or subschemes of C smooth obtained by removing in all fibers, well, except over closed points of spec Z, all irreducible components. So we remove a lot, well, not all, except one, because one I can treat with my problem, except one that is, and the one I keep, I want it to be geometrically irreducible. Okay, so these components are irreducible components of the smooth locus already, so they have multiplicity 1 in the fiber. They are smooth, but I have a problem if there is more than one. And I also, well, and so why this last condition? That is because if you have for P a point in C of Z, first I want to say, well, such a point P lies in a unique U. And why is that? Because this, if you draw a picture, right, this is spec Z, here you have your C smooth, and then you have generically an irreducible curve, but you could have here something, well, the double point, you don't include it, right, because it's the smooth locus, but you could have two irreducible components in a fiber. And, first I would like to say that this is the same as the Z points of the smooth locus, and that is because my model is regular. If a model is regular, then every section cannot go through singular points of the fiber, because in a singular point of the fiber, the tangent space will be two-dimensional, but that is the tangent space of the total space of this arithmetic surface. And the fact that it is not a smooth point means that the tangent map to the base is 0, but you cannot have a section and then come back with a map to get the identity on the base and somewhere have a 0 in the tangent map. So that is why the sections can never go through singular points of the fiber. So a section will go somehow, it has to choose this one or that one, right? And this is in every reducible fiber, it has to choose exactly one of the irreducible components, and it cannot choose an irreducible component where that is not geometrically irreducible, because so you could have irreducible components whose constant field is a finite extension of the prime field of the base. But then a section cannot go through that, also again because it has to go through a smooth point of this irreducible component. So for P, there is P selects exactly one geometrically irreducible component in each fiber. Right? I should also say that I have only problems with finitely many fibers. In such a curve, in such a model, there are only finitely many fibers that are not smooth, where there are singularities. So the fibers of the proper model are connected. So if there are several irreducible components, they have to meet, it's connected, so then they meet in singular points. My section has to choose exactly one irreducible component in each fiber, and I would like to introduce one little notation. Say that N is the product of primes Q of bad reduction of my curve C over Z. So then C to spec Z is smooth over Z1 over N. If I invert this N, it will be smooth. And the primes where I have a problem are the primes dividing N then. So that means actually there are finitely many of such open sets U, right? And you, well, this is very elementary to bound it if you would like to bound it. That's not the point. And if you want to find the Q points of the original curve over Q, this is the Z points of C smooth, and this is the same as the disjoint union over all U's of these Z points of U's, right? Because I say a section will just lie in a unique such a U, okay? So we can concentrate on one U and try to find all the elements of the Z points of U, and if we do that for all of them, then we have found all the Q points of the original curve. Good. There is a question.
Yeah. Why is the line trivial on U?
It is trivial because on such a U, you see, if I take the divisor of any generating section over Q, then it has this divisor in the fiber at the prime Q is just some number. Say it is 10. That means that my section has a 0 of order 10 along that component. Then I divide that section by Q to the 10, right? And I have solved the problem at that fiber. And then I do the others in the same way, and therefore it becomes a generator. Yeah? Okay. So then we have solved that. Yeah, so maybe it is also well, there is I have to keep track of the time. So when do I end? At 4:30? Eh? Yeah, okay. So there is an example in paragraph 8 of the preprint, the article with Guido. And it is of this kind. It is a genus 2 curve, hyperelliptic, is x to the 6 plus stuff. Right, well, that is an affine equation. Look in the section 8 if you want. This has Baird reduction. This n is, I think, 3 times 43, correct? And the fiber C smooth F43 is irreducible, but C smooth over F3 looks like this. It is 2 irreducible components meeting in 2 points. One curve has genus 0, the other one has genus 1, and that adds up with this loop to 2, right? So this is a possible reduction of a genus 2 curve. And here you would have, so here there are exactly 2 U's, because you can leave this component away, or you can leave the other one away, and that's it. Oh, here I should also leave out the double points, because I only looked at the smooth locus. Okay? Yeah? Good. So that is the, actually, yeah, it is good that I did not do this in my first lecture. Would not have been time for that. Yeah, then it's time to go back to what I had here in the beginning. So I want to go to this again here, this part, and to say something about how we control the closure of the Z points of T in the p-adic points. Right? I promised somehow that this would be not higher dimensional than before passing from J to T. If we do this in the Jacobian, and we have R generators for our, well, torsion-free quotient of the model Y group, then the dimension in J of ZP would be at most R, and I want now that in T it is not bigger. And this is because intuitively, because it is a GM torsor, it's a product of GM torsors, and GM over each z point of J, there are 2 to the rho minus 1 z points of T. So how do we do that? 2. Let me copy. Well, let me write it like this now. T of z is in T of z closure inside T of zp. And the claim is, well, how to describe this? Right, that is what we want to do now. Well, and to describe it, I said in my first lecture that I will use the bi-extension structure. I will use these two group structures. So that means that I cannot do this on T itself, because T lives over J. J is a group, but T is not. But T lies in a bi-extension. So let me, T lies over J. This maps to J times J dual connected to the rho minus 1. And on this I have this P cross to the rho minus 1 here. Pull back. And the map here was a kind of complicated thing. Identity on the first component and then oh, I haven't talked about the multiplication by m yet, right? But I will. Multiplication by m composed with translation over a point bi, which was previously denoted b of fi, I think, and then composed with fi. And here we do all the i's together, okay? And what is this m? Well, let me write a bit on my paper here. So if you do, J dual not is an open subgroup scheme of J dual, and this has a quotient, and we can call that phi of J dual. And this is a group scheme. This is what kind of group scheme is that? This is called the group scheme of components of J dual. And it is like a skyscraper sheaf. So it is trivial. This phi dual is trivial over Z1 over n, because there my Jacobian is a abelian scheme. The fibers are connected. Your curve has good reduction away from n. So your Jacobian itself is already the best possible what you can have. So there, this group scheme is trivial, but it has fibers, and it has finite étal fibers over Z1, Z mod nz, right? So at all the primes dividing n, I get something, a finite étal group scheme. And m will be the LCM, least common multiple, of the orders of, say, phi dual fq bar for q dividing n. So I want, you see, I need my map here to go to J dual not all the time. And so that is why I kill the potential problems by multiplying by the least common multiple of the exponents. Oh, okay, let me say order was a bit too much. Exponents, right? That will do well as well. Okay, good. So we have that. And yeah, so now let's recall the problem also a bit. We have this U here. This is the map J index B. Here we can now lift it, and we will call it JB tilde for the lift. And now we're going to look at residue disks, right? Because we want to find all the Q points, so all the Z points of U, but each such a Z point has a reduction. So now we actually, there is not a prime number P, well, I wrote it here, but we take P a prime of good reduction. P not dividing N, okay? And also we're going to take P bigger than 2. Okay, so those are the only condition on P. And then I have here, I take a point U, a little u, in UFP. And I would like very much to know how many Z points there are of U that reduce to this FP point. Right? If we can do that, then we have solved our problem. Okay, so this U, I need to introduce some notation. This goes to a point T here in the FP points of T. And now we are above the Jacobian, and there so the point of view we take is that we know the model Y group of the Z points of the Jacobian. So I can also say if, and over each point of the model of each element of J of Z, there are 2 to the rho minus 1 points in T of Z. So to check if this T is the reduction of an element of T of Z, well, that's doable. So, and if it is not the reduction of an element of T of Z, well, then this point cannot be the reduction of a Z point of U. So we assume that there is an element in T of Z, say T, tilde, that reduces to this T. Okay, otherwise we have no work to do. Okay, so and also this T tilde maps to a Z point in J that we call X of T tilde. Okay, I hope. Well, okay, so that is the. Yeah, I also should say that this. I have to introduce some notation, so let me do it here. This xt tilde is a Z point of J, but it's reduction. So if we look to which FP point of J this goes, it goes to, well, the image of this U, right? So this here I have the JB of U in here. This was the map JB, so this U goes there. So to indicate that this xt is a point in JZ that maps to JB of U, I put that as a subscript, JB of U, just to say it is in the residue disk of JB of U. Okay, that is the notation, and I will use the same notation everywhere. Okay, so then, yeah, now we have to do something. Maybe I show you how bad it is. Here, I hope this will show up more or less. So, can you read this a little bit in the back? Yeah? Oh, you don't need to see the details. So we choose a few things. There are Pij's there in equation 4.1. And these are, yeah, I cannot read it from here. So maybe you can better read it from a distance. Yeah? But you have to make some choices. And these are finitely many choices. Because the idea is to make for every point in J of Z, a point in T of Z above it. Right? That is what we want to do. But there are 2 to the rho minus 1, so we know, okay, there are not too many. But we want a formula for that, so that we can do that in a kind of systematic way, so that we can parameterize this set T of Z, and then if that parameterization is nice enough, we can say what the closure is in T of ZP. That's the whole idea. We have to parameterize T of Z. But now this T is not a group. It is like a subset of a bi-extension. It is a sub-scheme of this P cross to the rho minus 1. And this is embedded. This has two partial group structures. So it is actually a bit of a horrible situation where you are forced to, if you want to move around, you cannot move around in J. But you can, in J, in this product, you can move either in this direction or in that direction. And you want to stay on the diagonal somehow, right? So that is what is going on in this whole part, yeah? Here we make lots of moves like that and like that. And well, you can do this in the base of the. So this indicates each time the point here is in the product, right, of J and J dual to that power, and above is the point in the torsor. And actually, it's more complicated to write the image than the point itself, but that's a notational thing. But you have to use these partial group laws. Here it starts with A something. Here you see Ni, Nj, sum Nj times Sj, Ij or so. And here is a 1 or a 2. That means you do this either in the first variable or in the second variable. Right? And there are horrible formulas like that, 2 pages long maybe. So I'm not going to bother you with that. I will give you the result. What? We are trying to parameterize T of Z. So we want, in principle, we want to make a map from J of Z to T of Z. Okay? And there is no geometric map, because J, T is not a trivial torsor over J. So we want to make a map on the Z points that cannot come from geometry. Okay? This is not easy. Yeah, so we have to do that, and so not from geometry. But what we do is we make choices of well, these things that I showed. So you choose a basis of, so actually let me indicate that, right? So this J of Z, 0, that means this is the kernel of reduction at P of J of Z. Right? So we look at the kernel of the map from Jz to J of Fp. That is this notation here. This is free of rank R, right? And this here I use that P is bigger than 2. The kernel of reduction has no torsion. Okay? And we choose a basis, x1 up to xr, of this group. And then over each pair xi, xj, fi of xj. So then you can imagine that to look at, we were looking at this expression here. We want to make points in the here of this t. So that means points of the Poincaré torsor to the rho minus 1 that lie over a point that comes from J. So these are points where the x and y coordinates are related in this way. And you have to use these group operations in the Poincaré torsor to get there. Okay? Is that okay? Okay. Well, so let me write what comes out of that. So we get a map. Kappa Z, it's the name. And it goes from Z to the R, so that is this Z to the R here, to T of Z, and then residue disk of the little t, that was the image of this U under the lift of the map from the curve in the Jacobian. Right, so here is the little t, and I wanted to know which a Z point of U will go to a Z point of t, right? So I only look here at little t that come from T of Z, okay? And, okay. And now I want to know all the Z points of t that reduce to this little t, right? And we make this map, And it is given by these formulas that I had on the, well, on the page that I displayed. And it's not really surjective, but the image is big enough for what we want to do. But let me put the result. So that is one of the theorems of the article. So this is the theorem that is numbered 4.10. That doesn't mean there are 10 theorems or so. There are just some equations. And, okay. So we have the following situation. We have z to the r goes with this kappa z map, which is not geometric, to this residue. Well, it is still the integral points, the z points that reduce to the little t. And then we go to what do I want to say? Okay, let me put here a zp already. It goes certainly there, but it went to the z points. But here I have a bijection with zp to the g plus rho minus 1. And how do I get this bijection? This is by evaluating 1 over p times parameters of the local ring T, well, say the local ring O of T at T. So this is a local ring of dimension G plus rho minus 1 plus 1 for the arithmetic dimension. But that means when you take these parameters, the first parameter you take is P. And when you evaluate P and you divide by P, you can leave it out, right? That would always give you 1. So that we don't do. We take the G plus rho minus 1 other parameters. We evaluate them on the points here. That will bring you to P times ZP, to that number. And when we divide by P, we go to this. Okay? So, and this is, I write isomorphism. Actually, it's a isomorphism of p-adic manifolds, so that we will see some p-adic analysis, a little bit. Maybe more the kind of rings as you see in formal geometry. Okay, we have this. And the theorem says that this is contained, well, that is also not, this is also obvious. Z to the R is contained in ZP to the R, and that means right that this is a dense subset. And the thing is that this map, yeah, there is a unique kappa is kappa 1 up to kappa G plus rho minus 1. And these kappa i's are in a power series ring, ZP, and then let me write Z1 up to ZR. So they are functions on ZP to the R. And this I think we have seen this before. This is if I take the polynomial ring with variables Z1 to ZR and I p-adically complete it, I get this convergent power series ring, integral convergent power series. This is actually, if you take the affine space of dimension R over ZP and you complete it along its special fiber, then you get this coordinate ring, right? That is what you get. So this is if you would tensor it with QP, this is called affinoid ring. Affinoid. Okay, Tate algebra. Okay, so there is a unique, so what the theorem says is that this map kappa z that we made is actually given by a unique system of power series, integral convergent power series. Okay, and also it says that, and TZ T, the closure of what I wanted to know is the image of the kappa map. right? Because, yeah, and this I would like to stress that if you do classical Chabauty, you can also take this point of view that you say, well, what is the closure of the Mordell-Wij group? That you say, well, if in a sense you take points that reduce to 0 in the residue disk of the origin, but that residue disk, if you take p-adic points in that, actually has the structure of a ZP module. Instead of taking Z-linear combinations, you can also take ZP linear combinations, but that gives you the closure. And here we do not have one group structure. We have to work in this bi-extension, and with some work we can show the same stuff. And this is maybe related to these iterated integrals, because you have a log in one direction and in the other direction as well, right? And then when you do this you cannot do that on the diagonal. In our case, at least, we have to work then on this product. Okay, so the proof of this is well, if already the construction, the description of this kappa Z map is so horrible, then the proof cannot be short. So this is all of section 5 of the article, and this is 3.5 pages of atrocities, log and exp, right? So the idea behind it is that you have to say, look at say in an elliptic curve or in a Jacobian, right? Look at the map. No, I want to fix a point P, and I want to send an integer to n times P. And I want to view this as a function of n. And I want to see it as a kind of, analytic function of n. Then how do you do that? Then you have to say that this is, in the group law, it is the exp of n times the log of P, right? If you do that, then you can extend it to p-adic numbers. So if you can do log and exp, then everything works nicely like this. And we have to do this in this bi-extension. That means that you have to do this somehow in a relative situation, right? Because the P cross is an extension of A by GM, but over A dual. So you have to do this over a base that is not just the p-adic numbers, but say a higher dimensional variety or p-adic space. And that makes it a bit technical, but I think it is reasonably self-contained. We just use some formal theory, formal groups of commutative group schemes, and a reference to Honda. I think that is all we need. Okay, so then I have 10 more minutes. So then I can already, I can say what comes next. And then, so of course next comes the next theorem, but so also that needs a bit of introduction. And I want to do that in the last 10 minutes. So we have, let me go back to this Chabauty diagram now. We have U of Z U, right? This is the residue, this is the set we want to know. Yeah, we don't know it, we would like to know it. It maps to U of ZP, things that reduce to the little u over FP. This maps with the JB tilde to T ZP little t. That is all was defined like that. And we want to intersect this thing here. This is injective because it is the curve mapping to the Jacobian. Actually, I said P was a prime of good reduction. That means that even if I reduce mod P, the fiber of the if I reduce mod P, then I am not in a U of FP, U over FP is the same as C over FP because it is a prime of good reduction. And even in characteristic P, the map from the curve into the Jacobian is a closed immersion. right? So this is actually a very nice embedding. And one of the things that we will do is this comes at P from a closed immersion, right? And we do it on ZP points. But I want to take advantage of that there is some nice geometry with a closed immersion. And we had a description of this closure of the Z points, right? So the Z points here, oh yeah, this is in here, and this is the kappa map, right? So we said the closure of the Z points, that's the image of the kappa map. And this kappa map, well, if I compose here with my parameters divided by P, I go to ZP to the G plus rho minus 1, okay? And this is the map, actually, that is given by this power series, right? Kappa is kappa 1 up to kappa G plus rho minus 1. And what I want to say is that how are we going to talk about intersecting this with this, right? Or with the image of this? Now, actually, so there are two things. One is that we want to pull back equations for the complete intersection U into T at the point little u. So this was, say, analytic stuff, p-adic points, but here I talk about just local rings of u at the point u and t at the point little t, right? And that already when you map the t to the Jacobian, you see that the composition was locally a closed immersion there, and that of a smooth curve actually, right? So that means that you get a complete intersection. You can say, well, there will be equations, and what is the codimension of u and t? Well, that is the dimension of t minus 1, right? So we get g plus rho minus 2 equations here, right? And then we pull back these equations to zp to the r. To zp to the r. So instead of looking at the image of instead of trying to find equations for the closure of the Q points or the Z points and restricting those equations to the curve, we do it the other way around. Because we say it would be quite a difficult task to find equations for this image here. This might be a bit ugly, right? It is given by power series map. Who am I to get equations for that image? I mean, I am lazy, and I would like to do it the easiest way, and so I turn it around. Yeah? So, and the second thing is, we want to do this in terms of formal geometry. So that means rings like ZP, Z1 up to ZR. I want to get these equations. They have to have images in this ring, and then I can talk about intersecting them, right? And I will get an ideal in this ring, and actually this geometry, and then reduce mod P. This gives polynomials, right? The reduction of this ring mod P, so we get polynomials in Fp, Z1 up to Zr. And the whole thing we would like to do is to say, well, these polynomials, first of all, these equations, if you reduce them mod p for the curve, they will be linear, actually, degree at most 1. And I will explain that next time. And when you pull them back, it is really that you see that this is quadratic stuff. Then some of the equations, if you number them right and you choose your parameters right, they will be linear, but there will also be rho minus 1 quadratic ones. So we get a certain number of equations, elements in this FP, Z1 up to ZR, partly linear, partly quadratic, and you can feed this into a computer algebra system and then ask if the quotient by the ideal is finite dimensional as FP vector space. And if that is the case, then we get really nice upper bounds for the cardinality of that set UZ index U. Right, that is the game now. And again, my time is up, so see you tomorrow, or not, tonight, yeah. Questions? Here. Oh, yeah.
Why is J of Z0 torsion free?
Because P is bigger than 2.
Why does that mean it's torsion free?
That's a theorem that you can prove. I think there are many references for that. Basically, you can say, well, why is it not true for P equals 2? That is because minus 1 and 1 are congruent modulo 2. And that is the only case where something goes wrong. In the multiplicative group, I mean. Huh? Yeah, but this doesn't happen for bigger primes. If you are over a ramified discrete valuation ring, the condition is that the ramification index should be less than P minus 1. Right? So then you have the same result. If I can give you a reference if you want. A very nice reference. Okay. Hold on. No?
Okay, let's thank Bas again.
Just like yesterday, the evening sessions officially begin at 7:30, but the room will be available